This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Hey everyone, and welcome to our discussion. Today we're diving into the fascinating world of blackbody radiation using two different resources. We'll start with a simple interactive simulation and then move on to a more detailed explanation. Have you ever wondered what makes a light bulb glow or why the sun is so bright? It all comes down to blackbody radiation.
That's right. Blackbody radiation is the electromagnetic radiation emitted by an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. Think of it as a perfect absorber and emitter of light. The color and intensity of the light emitted depend entirely on the temperature of the object.
So the first resource we're looking at is a simple simulation showing the blackbody radiation spectrum. Lets you adjust the temperature and see how the emitted light changes. What are the key takeaways from this simple model?
The simulation visually demonstrates Wien's displacement law, which states that the peak wavelength of the emitted radiation is inversely proportional to the temperature. As you increase the temperature, the peak shifts towards shorter wavelengths, bluer light. It also shows that hotter objects emit more radiation overall.
That's pretty cool. So hotter things are brighter and bluer. But what about the intensity? How is that represented in the simulation?
The intensity is shown as a measure of the power emitted per unit area per unit wavelength. The simulation shows how the intensity changes with both temperature and wavelength. You can see that the intensity is highest at the peak wavelength and decreases on either side.
Okay, so the simulation gives us a good visual understanding. Now let's move on to the second resource, which provides a more in-depth explanation of the blackbody radiation spectrum. What are some of the key differences between the two resources?
The second resource provides more context and background information. It explains the underlying physics in more detail, including the concepts of Planck's law and the quantization of energy. The simulation is a great tool for visualization, but the second resource provides the theoretical framework.
So Planck's law, that's the equation that describes the spectrum, right? Can you explain it in a way that a high school student can understand?
Planck's law describes the spectral radiance of electromagnetic radiation emitted by a black body in thermal equilibrium at a definite temperature. It essentially tells us how much energy is emitted at each wavelength. The key idea is that energy is quantized, meaning it comes in discrete packets called photons.
Quantized energy, that's a pretty important concept in physics. How does that relate to the blackbody spectrum?
The quantization of energy is crucial because it explains why the blackbody spectrum isn't continuous. Classical physics predicted a continuous spectrum which would lead to the ultraviolet catastrophe infinite energy at short wavelengths. Planck's law, with its quantized energy, resolves this problem.
It's ultraviolet catastrophe. That sounds pretty dramatic. So Planck's law saved the day. What other important concepts are covered in the second resource?
The second resource also discusses the relationship between the blackbody spectrum and the temperature of the object. It reinforces Wien's displacement law and the Stefan-Boltzmann law, which relates the total power radiated to the fourth power of the temperature.
The Stefan-Boltzmann law, so the total power radiated increases dramatically with temperature.
Exactly. This explains why the sun is so much brighter than a light bulb. It's significantly hotter.
That makes sense. So both resources complement each other. The simulation provides a visual representation, and the second resource provides a theoretical background. What are some applications of understanding blackbody radiation?
Understanding blackbody radiation is crucial in many fields. It's used in astronomy to determine the temperature of stars, in materials science to study the thermal properties of materials, and in the design of lighting and heating systems.
Astronomy, materials science, lighting design, it's quite versatile. Are there any limitations to the models presented?
The simulations, while helpful, are simplified models. Real-world objects aren't perfect blackbodies, so their radiation spectra might deviate slightly from the idealized curves. Also, the simulations don't account for other factors that can affect the spectrum, such as the material's composition.
So real-world applications require more complex models. What are some areas for further exploration in this field?
Further exploration could involve studying the radiation spectra of non-ideal black bodies, investigating the effects of different materials on the spectrum, and developing more sophisticated models that account for various environmental factors.
That's a lot to think about. Thanks for this insightful discussion on blackbody radiation. It's amazing how such a fundamental concept has such wide-ranging applications.
My pleasure. It's a fascinating area of physics, and I hope this discussion has helped to shed some light on it.